All right, our last thing on conic sections. So we actually have a general form for any conic section, and it's this massive bad boy right here. So ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. So if you think about it, we cover all the cases. We cover x squareds, y squareds. We cover x's, y's. We cover a constant. We also cover when x gets multiplied by y, but really actually not going to deal with this case. And I'll explain that in just a second here. And then we set it equal to 0. That's our general form. And the degree of this equation is a second degree, right? Because you always grab the highest degree, which second degree term, second, first, 0th degree. So it's a second degree. And it's called a quadratic. Why is it not a quadratic function, though? Well, if this is the form for any conic section, don't we have some conic sections that are ellipses or parabolas going sideways? And would those pass a vertical line test for a function? No, they would not. Okay, so that's why it's just an equation and not a function. All right, and depending on what the values are for A, B, C, D, E, and F, will determine what type of conic section the equation represents. And I'm going to give you a guide to follow here. And it should make sense knowing all of our forms. And just like I said, the B is always going to be 0. So we're just going to totally get rid of that piece. We're going to ignore it for us because we don't look into the rotation of conic sections at all in Algebra 2 here. So what kind of rules do we need to follow here? Well, the first thing is, let's think about our circles. What needs to happen for a circle? Well, we need an x squared and a y squared, right? But what do the A and C have to be in order for it to be a circle? They actually have to be the same. So the A and the C have to be the exact same in order for it to be a circle. Okay, so I need to have an x squared and a y squared for it to be a circle. What about for an ellipse? What's different from a circle with an ellipse? Well, now they have the stretches. And so for it to have a stretch to make an ellipse, the A and the C have to be different. But they also have to have the same sign, right? Because for an ellipse, if we remember, it's x over a squared plus y over b squared, right? So the x and the y, they're both positive, so they have to have the same sign. They both could be negatives technically, but they have to have the same side. But they can't equal each other. They can't be the same thing. Because if the stretches were the same, if this was stretched by 3 and this was stretched by 3, it would be a circle. Okay, so that's where the A and the C have to be different. Well, where's another case where the A and the C have to be different, but that they might have a different sign? Well, that's for our hyperbola. Remember, they have to be opposite signs, right? Because the hyperbola, instead of a plus sign, we're going to have a minus sign there. Right? And it could be opposite. The minus sign could be on the x, and the y could be positive. So they have to have opposite signs, the A and the C. And technically, the A could equal the C, or the A doesn't have to equal the C here, because it would just be, it's either based off an ellipse or based off a circle where that hyperbola gets drawn. So either one works in that case. It doesn't matter. And then our last thing is our parabola. And what do we know about a parabola? Well, it's either x squared if it goes up or down. That means the y squared would be gone. Or the y squared would exist and the x squared would be gone, and that's where it goes either left or right. It opens left or right. So what do we know? That either the A has to be 0 or the C has to be 0. So basically, there can only be a y squared or there can only be an x squared. You can't have both, because if there's both an x squared and a y squared, then it's got to be either a circle, ellipse, or a hyperbola. All right, so knowing that, let's try to put these equations in their proper section. So the key is look for x squareds and y squareds. That's kind of the main thing. So if I look at this first guy, what's it missing? There's no y squared. So what does that mean? It has to be a parabola, because the rest of them have squares, an x squared and a y squared. Okay, so if it's missing one of the y squareds or the x squareds, it's always going to be a parabola. Okay, and we'll kind of get into later whether it's going to be up and down or left or right, whether it's going to be x equals or y equals. How about this next one? Well, I got an x squared and a y squared. The a and the c are different, so I know it's not a circle. And now I got to look at the signs. They're both positive. So is that an ellipse or a hyperbola? That would be an ellipse because they're both positive. They need to be opposite signs for it to be a hyperbola. How about the next one? We got, x squared and y squared. We got the same sign. So we're thinking a circle, but guess what? Opposite signs. One's a minus, one's a plus. So it's going to be a hyperbola. That's a trick one. But it's going to be based off a circle, but it will be a hyperbola because of the opposite signs on the x squared and the y squared. Next guy, x squared, y squared, different. So it's got to either be an ellipse or a hyperbola. Different signs, plus sign, minus sign. So that's also a hyperbola. Next guy, x squared, y squared, a and the c are the same. Plus sign, so it's got to be a what? A circle now. There we go. So we're really just looking for all those squares. That's what kind of keys us off. And the last one, we only have a y squared, so that immediately tells us that it's got to be a parabola, right? If it's missing one of the two, x squared or y squared, then it's got to be a parabola. So there we go. We just base those off. And what we're going to do with it in this section is we're going to write the actual equation in the forms that we're used to when we're given one in standard form like this. That's where it gets a little bit tricky. So what we need to know is our keys to all of our graphs. So this might be good to have to get ready for the test. So for our parabola, that deals with a vertex, with a focus and directrix. Remember, those are the same distance from the vertex. And then we also have lines of axis of symmetry. For a circle, there's a center, and there's a radius. Not much to that. For an ellipse, we have a center. We have a major axis that's the long way, and the minor axis, the short way. And we have basically 4 vertices for an ellipse, right? The ends of the major axis and the ends of the minor. And then we have 2 foci, which fall inside of that ellipse. And remember, the foci or the focal length would be from center to foci, right? It's from center to foci. Whereas the focal length up here for a parabola was vertex to focus. And for a hyperbola, remember, it's kind of based off an ellipse. So there's a center of a hyperbola, which is really the center of the ellipse. And then we have vertices, which are like the vertices of the 2 parabolas that the hyperbola makes. There's a transverse axis, which connects the vertices. There's the conjugate axis, which is the opposite one in the little rectangle that the ellipse makes. And we have a foci, the 2 foci, which are cupped inside each of the parabolas. And remember, the focal length would be from center to focus. Okay, lots of things. And then there's slope of asymptotes, which is really the b over the a, the rise over the run, and the negative of that. Okay, and then we have all those equations. So remember the circle. So it's kind of like an ellipse, but there's no stretch because the stretch is being taken care of with the radius here because it's going to be the same vertically and horizontally. So remember, to get the radius, we always just square root this guy. For an ellipse, remember that we have stretches now, and just be careful if the parentheses are not over the whole thing. Remember, if that's the case, that we really have to like pull out that square to find what that stretch is when they don't list the parentheses. And we got all our things listed up there. We got our hyperbola. Now we have opposite signs, right? So we got the minus sign now. So this is where it opens left and right. If we wanted it to open up and down, what would we have to do? We would have to take this equation and we'd have to flip-flop these 2 guys around. We'd have to make the y come first and the x come second if we wanted it to open up and down. And lastly, for our parabola, remember, we got to know our vertex form of these guys. Okay, the vertex form. All right, so let's take an equation and write it in standard form. Let's first decide what shape this is going to make, what conic section we got. Well, we got an x squared and a y squared, and the a and the c are the same sign, so this is going to be a circle. Okay, and if we remember, when there's x's and y's with it, what do we have to do in order to get it to our circle form? Remember, our circle form is x minus h squared plus y minus k squared equals r squared. Well, we need to get these factored forms of perfect square trinomials, so we need to complete the squares. So what I'm going to do is put my x's together, x squared minus 12x. I'll do the same thing for my y's. I'm going to leave some space so I can complete the square. So I got a plus y squared plus 10y. And then we want to move that 45 to the other side. So I'm going to subtract that 45 over. So I got negative 45 over here. And then to complete the squares, remember we take half of the b and we square it. So half of negative 12 is negative 6, and we square it to get positive 36. And that factored form would be x minus 6 squared, right? Because half of negative 12 is negative 6. So that's it, just kind of goes right in, and that's the nice part. Do the same thing for the y. So we take half of 10, which is 5, and we square the 5 to get plus 25. And the reason why I need to write these guys is to remind myself that whatever I do to one side of an equation, I got to do to the other side. So I also have to add that 36 and the 25 to the other side of the equal sign, which in turn gives me, well, this is really 61, and that would give me positive 16. So is that my equation of the circle? Yeah, I'm actually done. That would be it right there. And if I wanted to state the things of the circle, I would say that the center is at 6, negative 5, and that the radius is square root of 16, which is 4. There we go. What about this one? So similar. Got an x squared and a y squared, but now the a and the c are different, so it's not a circle, and the signs are the same, positive and positive. So this guy's going to be an ellipse. And if I think about my ellipse, it's kind of the same thing as a circle, right? But with stretches. So guess what we're going to do with this? Same type of thing. We need to complete the squares. So I'm going to write my x's together. 16x squared minus 32x. Leave some space. Do the same thing with my y. So 25y squared plus 100y. And I'm going to add this 284 to the other side. Okay, so let's complete the squares. Well, this gets tricky. Before we complete the squares, it's tougher to complete the squares if there's a coefficient on our second degree term. So we want to factor that out. So what I'm going to do is I'm going to factor this 16 out. And inside I'm going to have x squared minus 2x. And what I'm going to do is I'm going to complete that square after I factor that 16 out. So what would I get? Remember, we take half of negative 2, which is negative 1, and we square that to get positive 1. So I'm going to write my factored form here. So it's really going to be x minus 1, right, because half of negative 2 was negative 1 squared. And that 16 is out front still. Okay, and then I got to do the same thing to my green guy. So I'm going to factor out a 25. So I have y squared plus 4y. And to complete the square, I got to take half of 4, which is 2. So really this is going to be y plus 2 squared. And take that 2 and square it. So I get plus 4. And I still have that 25 out front. And then equals, this is where we have to be careful. So I got that 284. So let's look. So I got this 25 out front. I added this 4 on. I added this 1 on. I got the 16 out front. So do I just add 1 and 4? No, I didn't really just add 1. What did I really add? I added a 16 technically to this left side because I got to take that 1 times 16 to see what I really added. Same thing here. I didn't really add a 4. I added a 100 to that side. So I got to take that 25 times the 4 to figure out what I need to add on to the other side. That's where it gets a little bit tricky. So really this is 16 and 100. Added on to that 284 gives us 400. There we go. Well, I'm not quite in standard form of the ellipse because I need to know the stretches. And plus, what do we know about ellipses? They always have to be equal to 1. So I'm going to get it equal to 1 by dividing by 400. So I'm going to divide by 400, which means I divide this side by 400 and this side by 400. And remember, essentially what you're doing is simplifying. You're taking 16 over 400 and 25 over 400 and simplifying those guys. And when I do that, I should get x minus 1 squared over 25. And 25 over 400 should simplify to 1 over 16. So I still have my y plus 2 squared over 16 equals 1. And I'm still not quite there. Remember, I need parentheses around the entire x and the y terms. So remember, we almost got to like pull the square out of both these guys. You got to pull that square out. So my form in the end should be x minus 1 over 5 squared plus y plus 2 over 4 squared equals 1. Whew, that was kind of tough. Okay, so we're applying lots of things that we've learned so far. And lastly, let's do one of the parabolas, right? We're missing the y squared, so I know this guy's going to be a parabola. So if I have an x squared, what do you think I want to get by itself, the x or the y? Yeah, we want to get the y by itself because our general form looks like this. The x is squared technically. And so if I think about it, will I end up having to complete a square here as well? Yeah, because this is a factored form of a perfect square trinomial, so we're going to need to complete a square. And what might help is simply to put the 4x squared and the minus 8x on their own side. Maybe that's going to be helpful. I might just move this other stuff over to the other side just to take a look. I might not have to, but let's just try it. So I'm going to leave some space to complete the square there. Well, before I complete the square, remember I want to factor out that 4. So we got x squared minus 2x, and we take half of negative 2 and square it, which happens to be 1, because half of negative 2 is 1. Negative 1 squared is 1. And so really, what do I have to add to the other side? Remember, 4 times 1, so we have to add a 4 over here. So I really have negative 2y minus 6. And then the factored form of my perfect square trinomial would be x minus 1 squared. Still have that 4 out front. And that equals negative 2y minus 6. And I want to get the y by itself, right? I'm solving for the y. So let's add the 6 over. And I'm going to switch the side. So negative 2y equals 4 times x minus 1 squared plus 6. And lastly, divide by negative 2. So that leaves us with y equals, well, 4 divided by negative 2 is negative 2. And I still got my x minus 1 squared. And 6 divided by negative 2 is negative 3. I just divide each of those terms by negative 2. And there we go. There would be my vertex form. And technically I could, write the center. The center would be at 1, negative 3. And I could, find the focus. I could do all those things with that, get it in standard form. Okay, so a little bit of work that goes with it, but hopefully we're getting the idea of how to use this general quadratic.